We have CH2 double bond CHCl. You have lone pair of electrons here, and this can contribute to another resonance structure. See how you show the resonance structure. CH2 minus pair of electrons here, CH double bond Cl with a positive two lone pair of electrons. Remember, this is a charged species, this is a neutral species, and this will be more contributing to the overall structure. More contributing resonance structure is a neutral one. This is less contributing, but that is also present. Okay. Similarly, methyl vinyl ether, CH2 O CH3. Again, the same type of resonance structure. CH2 minus CH double bond O with a positive and CH3. Okay, so that is now the resonance effect with respect to aromatic compounds. This we have been doing so many times. See here, CH3 NO2 CH3. Resonance structures of these three will clearly tell you what is meant by ortho-para directing and meta-directing. Okay, if you draw the resonance structure, I hope you remember we have done this many times, repeatedly. What you can do is you can try by yourself. Donating the electron. I will show you once. One of them I will show you. At least some of the people who have not very keenly observed the last time. Now see how you shift the electrons. Let me draw it very clearly here for those who have not done it properly earlier. OCH3. There are two lone pair of electrons on this oxygen. Okay, you have double bond here, and double bond here. Look here, this is the electron is moving into the benzene ring. The electron is moving into the benzene ring. So here you are going to form two bonds. If you shift these electrons here, you are going to form two bonds. That's the meaning. I will draw it here. The result of this arrow will draw. See here. See, this is one bond already there. These two electrons, we are shifting between these two. See here, I'm putting it here. Two electrons here. What does it mean? It means an electron, it means a bond, OCH3. Okay, and remember there are two electrons here on this bond. Two electrons here. This bond. See this bond. Nothing but two electrons. Now look at this carbon. It has got 2 plus 2, again 2, 2, 2. So 5 bonds will be there. That is not correct. So what we do is shift it here. Okay, when you shift it, what we have to do is let me just remove this and see that I have put it here. So this carbon gets a negative charge. And see here, out of these 2 electrons, only one is remaining on the oxygen. Therefore, the oxygen gets a positive charge. So now let me remove these 2 electrons and show a bond only. This is nothing but a bond. Oh, sorry. It's just a bond. Yeah. Now, next, shift this over here, and simultaneously you can shift this bond to this carbon. That means the negative charge is getting transferred to the para position also. Here it is ortho. So these 2 electrons moving to form a bond here, a pi bond. And these 2 electrons are shifting to the para position with a negative charge. Next, shift these electrons over here. And this will be shifted here. And you get this resonance structure. These electrons are coming here. The double bond is formed here. Again, the double bonded oxygen. CH3, there is no change on this side. Please remember that. And negative charge. Always there should be one positive and one negative. Now shifting these electrons over here and taking this back. So what do you get? You get the double bond back and also not double bond. You get a single bond. Single bond here. Oxygen CH3 with 2 pair of electrons, and then there is one thing which I have to make it a little more clear here. Yeah, the double bond is getting shifted to the other side. That you have to remember. See this. So the first structure and the last structure, they are different. This structure and this structure are different because you have changed the position of the double bonds. So there are 5 contributing structures. There are 5 contributing structures. 1, 2, 3, 4, and 5. Okay. And what is the peculiarity of these structures? 1 and 5, they are of equal energy and they are the maximum contributing. 1 and 5 are the most contributing. Like you can say, like 60 to 70% will be these 2. And both will be equally stable. Okay. Out of these 3, 2, 3, and 4, this is the most stable one. Because this type of structure is known as the quinonoid structure. Quinonoid means you have, see, the double bonds are parallel and you have a pair of electrons here. So parallel double bond, and there is a, see here, this sort of a structure is known as quinonoid structure. So that is, out of these 3, this is most contributing. Okay, so this is the overall resonance structure of This is anisole. This compound is known as anisole. So similarly, you can write that of nitrobenzene. Only difference is in the case of nitrobenzene, the arrow movement is opposite direction. That's all. Try that by yourself. Okay? Please do it. Study this. This is the most important thing. Resonance structures is the most important thing which you should remember in your organic chemistry. Okay? Even in biochemistry, you are going to face this. It's the most important deciding factor in chemical reactions and biochemical processes. So don't forget that. Study that very clearly. Okay? So that is resonance structures. Let's look at next one, hyperconjugation. Hyperconjugation. Stabilization of double of the carbocation. For example, the best one is to explain this is look here. If I have a carbocation and then there is an H here, and H. This electron can sit here and form a pi bond. And you will get a resonance structure C double bond C with one hydrogen hanging here. One H here, one H here. Remember, it's not going anywhere else. Okay. So I can have two more CH3 groups here. CH3, CH3. This is the resonance. This is the hyperconjugated structure. Okay. Now, how many? See, if you have one methyl group, you can write three hyperconjugated structures using this hydrogen, and this hydrogen. So three resonance hyperconjugated forms for one methyl. Similarly, you have three methyl. That means total 9 hyperconjugated structures plus the original, there will be 10 forms. If you have 3 methyl, that is why this is more stable than a secondary. This is a secondary carbocation. Here you can form 7 structures. 3 from here, 3 from here, and 1 the original. And if we have only one methyl group, CH2, you can draw 4 structures only. If no methyl group, CH3, no resonance structures, you have only one form, no hyperconjugated structures. Okay, so remember, you should have a CH3 attached. Similarly, in the case of toluene, see here, toluene is having a hyperconjugated contributing effect. See here, a double bond, double bond, double bond. Now, these pair of electrons can come here. And simultaneously, this can shift here. What is the net result? Electron density of the ring increases. See this. Negative. And CH plus here. Double bond here. And H2 here. One H and two H. See that. How the methyl group is entering into hyperconjugated form. Now you can draw more resonance structures. So methyl group is electron donating. See the electrons are getting shifted towards the benzene ring. Okay, so this is one hyperconjugated structure. Similarly, you can have another compound. CH3, CH double bond, CH2. Okay. Now see here, I write CH2 here. I'll put one CH separate. Now shift this electron to this carbon and contribute it. See here. So it is CH2 with an H plus hanging here. It is not going anywhere else. This forms a double bond. CH, CH2 with a pair of electrons here. So this is what is called a hyperconjugation, right? So it is something like this. See here. What is happening is this carbon is having a pi bond. The pi bond is in this direction. Here also there is a pi bond. Now look at the orientation of this carbon and hydrogen bond. See, the orientation of this carbon hydrogen bond is something like this, which is aligned with these orbitals. Okay, at one time or the other, this will be aligned. Therefore, there will be a bonding interaction between these two. Okay, and that time this breaks. So effectively what is happening is there is an interaction of electron over here, here, and here. So there is a continuous interaction of electron between these three orbitals. That is what is called hyperconjugation. Okay, right. So that is, so you can explain the stability of different carbocations based on hyperconjugation. Next one is steric effect. I'll wipe the board. Steric effect. What is steric effect? Crowding, affecting the reactivity and stability. Crowding, affecting the reactivity and stability. Reactivity. Reactivity and stability. That is what is called steric effect. For example, H, CH3 and CH3. This is less stable than this. Oh, sorry. CH3 here and CH3 here. Why? Because the CH3 are far away from each other. So this is cis-butene and this is trans-butene. Trans-butene is more stable than cis. Okay, so that is because the bulky groups are away from each other. Similarly, we can have in the case of butane molecule. Look at the conformation of butane molecule. This is butane, CH3 and CH3. This is one conformation. Okay, now see H, 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 and H. And look at this conformation where we have CH3 very close to each other. This is the eclipse form. This is more stable. Less stable. Why? The CH3 are very close to each other. So this is the example for another example for this one. What is that? Steric effect. Okay. Similarly, it affects the reactivity. For example, basicity of amines. Basicity of amines. Okay, dimethylamine is more basic. Dimethylamine. What is, now see here, the order of basicity, CH3 twice NH is more basic than methylamine, CH3 NH2. And uh, and then this is the order of basicity, CH3N. Okay, here, see, generally what we expect is we have CH3 N, CH3, CH3. So inductive effect will increase this. Okay, inductive effect will increase the electron density on the nitrogen. So you expect this to be more basic, but it is less basic compared to methylamine or dimethylamine. The reason is, even though there is an increased electron density here, the H plus is not able to approach here because of the presence of these bulky CH3 groups around. Let me draw the CH3 separately. C, H, H, H. Then you have C, H, H, and H. Again C, H. Now see, here is a lone pair of electron. The approach of the proton over to here is hindered, is blocked by the presence of CH3 groups around. Okay, that is less effective in this case. Here there is less, and in dimethylamine it is more basic than methylamine due to some other reason. It is some other reason. So that is the presence of water molecule, solvation effect. Okay, so this is the order of basicity. This is most basic, this is less basic, and this is least basic, even though it is having more number of methyl groups. It is a steric effect which decides the basicity. Okay. Another effect on carboxylic acid. See here. This compound, COOH, COOH. This can react with water and form the benzoate anion. This can form the benzoate anion, COO minus, plus H2O, H plus or H3O plus. Now the pK value of this is pK value is 5.05. 5.05. Suppose I have another compound. Look at this compound with two CH3 groups here, not CH3, two T-butyl groups. Okay. Now, if they say under same condition, benzene ring. Under the same condition, COO minus plus H3O plus. pK value is, the pK value is 6.25. So less acidic. Why? Same reason. This H plus, the water molecule cannot come and take it out. Approach of this is prevented by the presence of bulky groups here and here. Okay. Yeah. So this is again due to steric effect. Again, there are so many other reactions also which you can think of, which is affected by steric reasons. Okay, that's good. Now next is reactive intermediates. Reactive intermediates. We have talked about carbocation. I don't want to repeat the same thing. Carbocation. Okay, same CH3 plus, C2H5 plus. All these are carbocations. Similarly, CH2 double bond, CH single bond, CH2 plus. Aryl carbocation. All these are stable. Okay. Then, how do you form these? How do you form the carbocations? By heterolytic bond fission. By heterolytic bond fission, you can form it. Okay. Of course, this is not very easily formed like this. Plus Cl minus. Okay. This will occur only in presence of Lewis acid catalyst, LCl3. But this carbocation can be easily formed. C plus Cl minus. Okay. Similarly, CH2, CH, CH2 Cl. No, one second. CH3 here. No, one second. Here. Yeah, it is CH3 single bond CH2 CH CH double bond CH2. Yeah. So this is propene. If you treat propene with a little acid, see here it will form a carbocation. You will get a carbocation on the central carbon. CH3 CH single bond CH3 with a positive charge. Okay, this is an example for addition reactions, which we are going to see later. Okay, now the structure of carbocation. See, this is the structure of carbocation. I will put it like this. See here, trigonal planar. There will be 3 sigma bonds in the same plane, and then there is an empty orbital. Okay, so this is R1, R2, R3. If you rotate it, it will look like this. Empty orbital is perpendicular to the plane of the bone. R1, R2, R3. So trigonal planar. Okay. Stability. Tertiary carbocation is more stable than secondary, more stable than tertiary. Why? Why? Hyperconjugation and inductive effect. Okay? Hyperconjugation and inductive effect are the reasons for the stability of carbocations. Okay, similarly, benzylic carbocation is very stable. This is very stable. Why? What's the reason? Resonance effect is a one-word reason. Resonance effect is a one-word reason. Okay? And that is not enough. Please draw the resonance structures of this. 1. So positive comes here. Then 2. Positive comes here. 3. Positive comes here. So you can write 4 or 5 resonance structures for this. Please draw the resonance structures and explain. Okay, so this is carbocation. Now let us look at carbanion. Carbanion. Species with a negative charge. CH3 minus. Okay. Now here what happens is you should have a bond breakage. Suppose you have a bond like this. It should break in this direction. So what is needed is you require less electron negative atom here. An atom M with less electronegativity, for example, magnesium. So methyl magnesium bromide. This will dissociate into CH3 minus and MgBr plus. Okay, this will dissociate in this way. So this generates a carbanion. Similarly, you can generate carbanion from lithium compounds. methyl lithium. That also generates CH3 minus. Okay, so organometallic reagents will generate carbanions. Another example of generation of carbanion, you take acetylene. Acetylene. Okay, and react with a strong base like NH2 minus, sodamide. This lone pair of electron can catch this